In this video, I'm going to tell you about functions of several variables. So we're going to really get going on multivariable calculus in the sense of like what you expected when you signed up for the course. And now at this point in the course, we're going to be studying functions that take in multiple variables and give back one real number. Okay, so the fact that it gives you back one real number is the part that makes it real valued, and the fact that it takes in n variables is, function of multiple variables. Okay, now for us, we are mainly going to focus, at least for now, focus on the case where z is a function of x and y. Okay, but we will also look at other scenarios that could take in more than just the two variables. But I'm proposing that you maybe have seen situations that depend on two variables before, right? We know that the area of this rectangle is equal to x times y, which means that I could say that, the area is a function that depends on both x and y, and it's given by x times y. Right? We've seen that before. We just haven't written it as a function of two variables. Another example of a function of two variables that you've seen before is like the temperature of an ideal gas. Okay, I know a lot of y'all have a lot of experience in chemistry, honestly probably a lot more experience in chemistry than I have, but you know that PV equals N times R times T for an ideal gas. And now I'm going to assume that the amount of gas is held constant. I could say that the temperature is going to be equal to, well, that would be PV divided by N and R. But if N and R are both constants, I could say 1 over N times R times PV. Okay, and if I wanted to write this as a function of two variables, I would say, okay, temperature, which depends on both pressure and volume, is equal to 1 over NR times P times V. Okay? And these are a couple of things that you've seen before in the past. An example of a function of three variables that we've seen already is distance from the origin, right? If I have some point in space, P, or like a vector that's emanating from the origin and going to point P, and P is the point, x0, y0, and z0, we know that that distance from the origin that I'm going to color in here, and that we could call d, and we could say that the length of d is going to be the square root of the x coordinate squared plus the y coordinate squared plus the z coordinate squared. And I guess that in general, if, p was x, y, and z at any point in space, d would be a function that would depend on both x, y, and z. And that would be an example of a real valued function of three variables. Right? And then I'll also tell you an example of something that is not a real valued function that would take in multiple variables, like something we're going to call a vector field later in the class. Is like, okay, you're a person and you're standing at a point in the plane, I guess you've got arms too, and you feel some sort of wind, right? And maybe the wind is a vector and it is blowing, I don't know, maybe it's cold right now, maybe it's a north wind, so maybe you're feeling that wind at that point in space, or on the plane, pardon me. And that's going to be something that takes in an x and a y and gives you back a two-dimensional vector. We can just assuming the wind is not blowing down or up and it's just blowing kind of like parallel to the surface of the earth. That's going to be a vector field. And because the function would give you back a vector, that's not going to be a real value function. That's not something we're studying right now, but it is something we will study later on in this course. All right, now let's talk about graphing z equals f of x and y. Unfortunately, drawing graphs of these things is not as easy as it was in 2 dimensions, where it was just like, kind of plot points and connect the dots in the worst case scenario. This is going to require a little bit of drawing, right? And, my art skills are not great. but they have gotten better over time. And so I am telling you, it's not super important in this course that you be able to draw wonderful sketches of three-dimensional things. But if you just are intentional with what you're doing and you give it a little bit of practice, you will get better. Okay, so the first one I want to graph is the f of x and y is 5. Okay. This is going to be very similar to, in the y equals f of x case, the function f of x equals 5. Okay? And we know how to draw that. Okay, that's a constant function, so I go over here to where y is equal to 5, and it's the set of all points where y is equal to 5. And in some way, the f of x and y equals 5 is going to look kind of like this. So I'm going to start by bringing in a xyz space, axes, and drawing a parallelogram. You're going to have to decide where z equals 5 is on the z-axis, and you're going to draw a parallelogram that's going to be parallel to both the y and x axes, and then you're going to kind of just color it in and maybe, give it some, you see how I colored on top of it in yellow to get rid of part of the z-axis to give you a little bit of perspective, and then you get yourself, okay, it's a plane, it's going to extend infinitely, but if you want to draw a nice picture of it, you're going to want to just draw part of it. And that would be a graph of f of x and y is equal to 5. Another one I want to graph for you, because it's pretty easy to draw, is f of x and y is 5 plus x squared plus y squared. And in some ways, this is very similar to the graph of f of x equals 5 plus x squared. And we are very familiar with how to draw something like that. We start at 5, and then we draw the graph of y equals x squared. Shifted up by 5. So in some sense, our surface is going to look like that. And so I'm going to start by bringing in a 3D axes. I'm going to decide where 5, maybe it should be right there. And then I'm going to draw something that kind of looks like a parabola. And then I'm going to give it some depth by, putting some ribs on it. So I'm going to put this one in here, that one in here. Might even put a little dot there for reasons that you'll understand in a little bit. And I might also, I'm going to put one more over here. And then, some more color might help. And I'm going to come back to this drawing here in a couple minutes, but that's what it's going to look like. Now I'm going to tell you about level sets and contour maps. So definition of a level set is basically the set of all points in the domain that map to a given point in the range, okay? Or I guess the codomain. And the level set could be empty. But let's look at an actual example here. We already know a lot about the function f of x equals x squared, so let's consider the level set f equals 49. Okay? That's going to be the set of all x's where x squared is equal to 49. And we know that that's the set that has -7 and 7. Okay? The level set for f equals 0, that's just the set that has x equals 0. And the level set for f equals -1, well, that's empty because there's no real number that I can square and get -1. Okay? And so that's an example of a level set. Let's look at one of the functions that we've already talked about and get a level curve. Because if z is a function of x and y, so suppose I'm going to have a function that takes in 2 variables and gives me back a real number with f of x and y equals 5 plus x squared plus y squared. Okay, we just looked at that. We drew a picture of it. I'm going to want to go back and look at it in a moment. And we'll look at the level set, say, f equals 9. Yeah. So let's look at f equals 9. Okay. That's going to give me 5 plus x squared plus y squared equals 9. Okay? And if I start simplifying on this, I'm going to get an equation for a curve. You look at that and you're like, oh, x squared plus y squared equals 4. I know what that looks like. That's a circle centered at the origin with radius 2. That's not the worst. Okay, so, that's 2. Okay, that's going to be the level curve corresponding to f equals 9. Now, oftentimes because drawing the graph of these functions, z equals f and y, can be pretty difficult, especially in times before we had good graphing software, kind of the next best thing was to draw a contour map. And contour maps are still useful to us because we can still draw lots of conclusions about the original function based on the contour map. And, things we can't draw by hand, we might be easily able to draw a contour map. Contour map depicts the level sets of a function on its domain. For our purposes, we're going to be looking at contour maps that are depicting level curves of a function z equals f and y of x and y basically on R2. So I'm going to bring in that previous example. I'll say, well, graphing that level curve was just kind of the beginning of making a contour map. Okay, I'm going to clear out this computation here because we already did that. I might be interested in the level curve f equals 5. Start with that one. Okay, that's going to be where 5 is equal to 5 plus x squared plus y squared, which is going to give me x squared plus y squared equals 0, and that's going to only happen at the origin. So I'm going to put that right there, f equals 5. Okay. Then I could also do, what about, what do I want? I think 21? Yeah. So if I had f equals 21, sure, there might have been another number closer that would have made sense, but I'm going to have 21 equaling 5 plus x squared plus y squared, leaving me with x squared plus y squared equals 16. We know how to graph that. Okay, that's going to be over here at 4. It's going to be another circle. Now I'm going to need to extend these axes and draw a circle with radius 4. And there we have a contour map with 3 contours. Okay, realistically, a contour map should probably have more than 3 contours on it, but I know that the more of these circles that I draw, the worse it's going to look. And so you see that this is the beginning of a contour map. Okay? And if you want to see a different example of a contour map, I believe the next video in this playlist has a very common example of one that you've probably seen before. And the last thing I wanted to show you before I let you go was the connection between the contour map and the graph of the function. Okay, notice how those contours that I've drawn there, okay, it looks like I drew 3 circles on the original graph, but the contours correspond to, kind of horizontal slices of the graph along the z-axis. What horizontal means, but, if we cut along the z-axis and take a cross-section, that's going to end up being a level curve, okay? Or you could look at it as kind of like squashing the entire surface down onto the xy plane, tracking how high each thing was. It's like a topographical map. Okay, and I think that's all I have to say about functions of several variables. Next time we'll come back and we'll actually start taking some derivatives of these things and doing things that feels more like calculus.